Okay, let's first address two small issues. What we have left in the previous implementation of the backpropagation algorithm and that are discovered, exposed in the test procedure we will discuss shortly. First, I was um, I was made typos. I have done this equation to compute the gradient with respect to a. But actually, as here, for the sigmoid function, the equation accepts the current value of the function rather than the input of the function. So I should have written h rather than a here to compute the gradient with respect to a. And secondly, after we have computed the derivative of the model parameters, these are the parameters, we need to save the parameter somewhere because we will then use this gradient to adjust the parameter values. With these two adjustments, we are pretty much ready for performing the subsequent optimization algorithm. Well, we discussed shortly about how the test of this backpropagation algorithm. I have written two functions to test the numerically test the derivative of the two model parameters, which is structurally very similar to what we have done for computing the gradient with respect to the final output of the network. Rather than computing the derivative with using the output, we will compute the gradient with respect to the model parameters. So for these two test functions, the inputs are the data and the model itself. Well, we calculate the original loss function without changing anything and allocate a numerical derivative cache buffer. Then we will adjust one element by another for the particular parameters we want to test. Here for W, we change the we save the value of the current W element and change it by a small amount, and then use adjust the modified network to process the data, make predictions, and use the loss function to compare the prediction with the desired annotation and to compare how that loss has changed with respect to the original loss. Using this difference, we calculate the numerical gradient of the loss function with respect to not the gradient, the derivative of the loss function with respect to this particular element, the ijth element in the W matrices. And lastly, after having done this modification check for each individual element in the matrix, we return the numerical gradient. We do the same thing for the U parameter, and those are two adjustable parameters in the neural network. In this simple neural network, we forgo the bias part for now. So let's see how that works. If we define this, and we construct neural network function model. We use the model to make a prediction, and we do the derivative of the prediction. And if you recall that we have squeezed the output for the network so that it is a vector rather than two-dimensional with one dimension, a singular dimension matrix. But here, to make this matrix multiplication doable, we need to convert the vector back to a two-dimensional matrix with one singular dimension, which is a very tall matrix. So we create a new axis in the matrix and populating the content of the vector into the column of the matrix, into different rows of the matrix, and in each row it has only one element, of course. And we perform the backpropagation using this derivative, this gradient vector, and we take out the analytically computed derivative with respect to W element, that is a gradient with respect to W, and that for U. And we also calculate the derivative using numerical methods. And then let us compute the computed derivatives. So they are very similar. If we have a look at the difference, we have a very small difference. That means the computation is probably correct. We can also do the same for the U matrices. Look, U matrix is has only one column in each row, and the difference is also very small. So that verifies our implementation of the backpropagation algorithm.